some mathematics. Progress. What do we have today? We have some correct ingredients to make the fried mathematics. Okay, we have the people here. Not so many people today because some people just say, no, it's bad weather. I cannot go to campus. And I just stay on the campus, yeah. Okay, so today we are going to get another formula to approximate our derivative. The derivative, we already have the forward difference, backward difference, and center difference formula, if you remember what you have learned last time. And this time we are going to use the Richardson's extrapolations to get another formula for the derivative approximations. And then let's go back to take a look at what we have last time. So last time we have already got the formula, and then we analyze the errors coming from the rounding off. And then we get the total error. The total error has two parts. One part is the rounding error. Another part is about, scroll down. Another part is the truncation error for the center difference of approximations. And for this week's homework, I'm going to post a tweet today. And I think the homework should compose two parts. The first part, I will ask you to analyze. So for this class, and then in the class, I have already analyzed the error for the center difference formula. So in the homework, I'm going to ask you to analyze the total errors for the backward difference formula. And you need to figure out the optimal step size h. And so if you want to figure out the optimal step size h, and then you need to get the derivative of the total error, and then let it to be 0, and then find out the critical value. And that's it. But it's for the backward difference, and then you will have another optimal h. And so let's see. I have some conclusions from the last time. The conclusion is here. And I just say, okay, so let's take a look at the error. This is the first order h, and then this is second order of the h. And if the h is like, let the h to be like step size to be 0.1, and then this one is 0.01, and this one is the magnitude is just 0.1. So if you take a look at the picture, and then we find out that the center difference is a better approximation, and it's more parallel to the slope of the f point x, that is the negative. And we will find out the reasons here because the error here is h to the order 2, and this is just the order 1. So today we are going to find out some formula which has a higher order of h in the error time, which means that we would have a more accurate approximations to that derivative. During this process, and then you will also find out the approximations formula to the second derivative. So all the things here is approximating to the first derivative. And in this process, we are going to derive a formula to approximate the second derivative as well. And some students ask me that, so what you have here is to use the Newton's formula to derive the center difference formula, forward difference formula, and the backward difference formula. And one student after last class, he asked from the 104A, he learned something similar to this. Or other classes, he learned something similar to this. And the professors there is using another way to approximate the whole things. So the professors is in the other class is doing the Taylor expansions around the x0. And then after doing the Taylor expansions here, and then just getting the derivative of that Taylor truncated Taylor series. Yes, you can do that. Yes, you can do that to get the to derive this formula. So actually, today we are going to derive the Richardson's extrapolations formula with the Taylor expansion. And so let's see. So we call this method as the Richardson's extrapolations. So first, let's take a look at this approach, and it's throughout the Taylor expansions. So let's recall what is the Taylor expansions for a function, and it's a function which is infinitely differentiable. Oh, it's recording, good. And it's infinitely differentiable set the neighborhood of a real number A. If we want to expand the fx, get the Taylor series around the A, and that is it looks like this. The Taylor expansions around the A, it should be fx, and then equal to sigma sum infinity and equals to 0, and then fn, and then a, and then n factorial x minus an. This is the Taylor expansion, and here I am going to get the standard difference formula with the Taylor expansion. Wait, there's some things here I want to mention. So that should be in another note. I will mention this later on, and I will come back to here later on. But here, let's derive the standard difference formula first. So with the Taylor expansions here, we are going to derive the standard difference formula. They should be the same as the previous class. But here we are going to just use the another methods to derive the standard difference formula. And so if we want to get the Taylor expansions around the x0, and then we get the f evaluated at the x0 plus h, it equals to, so we are just doing the expansion around the point x0, and then we got this. So this is the first point, and then this is the first derivative term, and it should be h, because let the things here be n equals to 1, and then I get first derivative, and then this is just one factorial, and this one, the x, is the x0 plus h, and then the a here, I'm expanding the getting the Taylor series around the point x0. So here this is x0, this is x0 plus h. So I got x0 plus h plus h, and then minus x0. So I got h here. Does it make sense? So I get n equals to 1. So let me see. I just write that down here. So for this item, it's just the Taylor expansion, but it's the Taylor expansion around the point x0. And here I got, so in this equation, I get this one is x0. And for the first item here, n equals to 1, and then I got that item. And then the second item should be plugging in the n equals to 2, and then I got the second derivative, and then 2 factorial. And then so these things here for this expansion, this one is x0 plus h. So this one should be h squared. And the third derivative, and then h is cubic. Am I right here? Yes, it's correct. And the fourth derivative, I just expand as many as I can, but I would use the 3 dots to represent the things coming after the terms, because it is infinite, so I cannot write all the things here. x0, and then 4 factorial, h4, and then 5 f5 x0. So I'm going to expand now, write out the terms as many as I can, in case that I need several terms in the expressions. So so the next things I'm also doing the Taylor expansions here, and then but this Taylor expansion is for the f0 minus h, which means that I'm going to just change this x to the x0 minus h, and then that's the same thing, x0 minus h, and then this one is x0 minus h, and so here I got f0 fx0, and then plus f prime, that is the first derivative, and then 1 factorial. But here you should pay attention to here. We have a sign change here. So here is x0 minus h minus x0. So I got negative h, and then to the other one. So here I got minus h. And you need to be very careful. And you also need to know this for your homework and your exam. So here for the second term, I just got second derivative x0, and then 2 factorial negative h and then square. And this is the third term, third derivative, and then negative h third, the third order. So order 3, and then this one it should be x0, 4 factorial negative h 4, and then plus the 5 factorial fifth derivative, and then negative h 5, and then so on and so forth. And if you take a look at here, this is the negative h and then square, and then it equals to h squared. And I just put the negative size to the from, and then I will get a minus f prime x0. And this is just minus h cubic. And then this is just h to the order 4. This is minus h5. So I'm going to change the expressions a little bit. This is just the same as h. And then doing the subtraction. And then for the E1 terms, the E1 index terms or E1 order term, I got h squared. And this is the odd order term. So I got the subtractions here, and then h3. And the E1 number term, E1 order term here, and then it's just the h4. And then once again, I got the odd order term, h5, and then I got a subtraction size here. And then now I'm going to do the subtractions. I have two equations. I have the equations 1. I have the equations 1. I have equations 1. I have the equations 2. And I'm going to subtract the 2 from the 1. And it should be subtract the 1 from the 2. Wrong index. Okay. Okay, subtract 2 from 1, and I got fx0. What's going on? Okay. I'm going to subtract the things from the 1, and then I got fx0 plus h, and then subtract the fx0 minus h. And if I do the subtractions, if you take a look at here, if I do the subtractions, doing the subtractions here, and then this would be cancelled by this. But this is just a double f prime x0h. And then for the E1 term, it's just go cancel away. And then this one for the odd order term, and then we just double the terms there. So at the end, we get, we have on the right hand side, we just keep, so I just say this cancel away, this cancel away. The E1 number term just get cancel away, cancel away, cancel away. So at the end, I got 2, and then f prime x0h plus, so everything get double for the odd index term. and then there's some terms coming after it, but all of them should be all order 10. And then now I'm going to divide the both sides, dividing both sides by 2h, and then I got this f0 plus h minus f0 minus h, and then divided by the 2h, and then I got this. And then on the right hand side, I got f prime x0 and plus f cubic x0, and then 3 factorial h squared, and then fifth derivative, and then h4, and then so forth. And this is what I got. And this means that, and this is actually means that I'm going to move the terms around. And then this means that the f prime x0, and then it could be approximating by this formula, and then with the error here. The error is just the third derivative, h squared, and then 3 factorial here, and then minus fifth x0, and then fifth h4, and then so forth. So here, this is the something we have already mentioned in the last class, and this is the standard difference formula. But this is nothing new, but with another methods to derive it. In the last class, we used Newton's format, but here we are going to use the Taylor expansions. That is another way to derive this formula. And if you take a look at the area here, it's also with the magnitude h squared, which we just ignore the h4, h6 here because they are with smaller magnitude. So the dominated term should be the h squared. So I have the area term here is with the big O h2. Does it make sense? So if you take the step sign as the h equals to 0.1, right? And then this is just a 10 negative 2, and then this is 10 negative 4, then 10 negative 6, and they are way smaller than the 10 negative 2. So we can just keep the dominated items here to say our error is around this size. Any questions here? Why do we need to skip the everything's after it? Okay, if you don't have any question, no, you just or getting your hair right way. Okay, so this is subtraction. This is subtraction. Subtractions. If you do the subtraction, subtracting the 2 from the 1, and then we get the standard difference. So what about we do some summation here? Doing the summations for the 2 and 1. Let's do the summation, okay? But if you do the summations, and let's see, just take a look at here. What do we have? If we do the summation, erase the highlighter only. We have the equation 1 and equation 2, and then if we do the summation, and then I'm going to do the summation here. And then you will see now the cancellation is happening in another way. So this will be canceled away with this one. And then the other odd order terms will be canceled by the things in the second equation. And then odd order term can be canceled. But we keep the U1 order term here. This is U1 order with the order 0. Do you see that? Because this is just the h2 the order of 0. This is h2 the order of 2. So let's do the summation and then to see what do we get. So we just try out to do some subtractions and then summation, and then to see, do we have some formula, or do we have some can get some things out of the result. So we just do the summation here for that Taylor expansions. You will get some homework to practice on this. So let's do some summation here, and then we just keep the even order 10 because the odd number 10 or order 10s get cancel away. Am I right here? I think we should have, so let's see, we should have the two factorial here, and then we also have, so here this time should be the 4 derivative, and then 4 factorial h4, and then here I got 6. I write one more time here in case we need this one. So now let's do some thing here. So the idea of approximating the derivative is to use the raw data. So the raw data is just the f value, the f functions value. So here we have, this is raw data, and then this is also raw data, which means that we get the functions value. But we want to get some approximations to that derivative with the use of the raw data. So I'm going to move the raw data to one side, and then we got this. So I'm going to move the raw data to one side, and then I got fx0 plus h plus, so there's one thing here, and then that is subtract fx2 fx0 plus fx0 minus h. And then on the right hand side, I should have the things remaining here. And the one more items. And that is the last item I have. If I want to include it in the expressions. Here, okay, good. So what do I have here? So on the left hand side, it's the raw data. And then on the right hand side, I got the second derivative as the first item. This is the 4 derivative, this is 6 derivative. So here I'm going to divide both sides by 2h squared. And then I will get rid of the 2h. I'm going to just divide those things by h squared. And then I can get rid of the h squared here. And here, let's divide both sides by h squared. Divide both sides by h squared, and then I got on the left hand side is this formula or expressions. Minus h, and then divided by h squared. So on the right hand side, we have 2 times 2 divided by the 2 factorial is just 1. So the first item should be the second derivative, and then the second item should be the 4 derivative, and then that is just the 2 divided by the 4 factorial, and then it should be just equals to 4 times 3 times 2, and then we have the numerator in the 2, so here it is just a 12. And but here we divide both sides by h squared, so h4 divided by h squared, and then we just have that h squared here. And then we have the 6 derivative as well, and then it should be the 2, and then you have 6 factorial. It should be 6, 5, 3, 4, 3. And that's a big number. I'm not going to calculate it. But for this order here is h6 divided by h2, and then I got h4. So now actually you get an a formula to approximate the second derivative. So I'm going to rewrite all the things here, and then you will see the formula to approximate a second derivative. So by so far, this is not called Richardson's extrapolation. This is something we just want to mention when we are doing the Taylor expansions. So here on the right-hand side, I just move the things around because I would just write the exact value on the left-hand side, and then I will write the approximation formula on the right-hand side, and with its error. So the error, it looks like this, and the h squared, and then the six derivative. And once again, you will see the dominated error here. Error turns here, it should be h squared. So here I'm going to write this one. So this one, we call this is the second order approximations of the second derivative. And the order term, the error term is in the magnitude of big O h squared. Does that make sense? Any question here? This is not the Richardson's extrapolations yet. This is some things we want to mention, or we want to get from the Taylor expansions. No more questions? And with this formula, actually we would get the extrapolations for that. Something is missing here. So the next should be the Richardson's. Okay, let's see. So I'm going to write down the errors in another way. So I'm going to denote this as this is just a constant, right? I'm going to use the C2 to denote it. And then this one, I'm going to use the C4 to denote it, because I'm using the C2 because here is just it's corresponding to the order 2 coefficient. This is corresponding to the order 4 coefficients. Okay, good. I'm going to use this to denote my the things I have here. And for the second order approximations of the second derivative, and sometimes we would use the notation because this is finite difference. So we have the capital D here, and then it's with the step size h. And because it's second derivative, and then we got the, we use the 2 here, the superscript here, to denote this expression. So I have, this is the second order approximation of second derivative, and then this is the formula to approximate it. This is quite important. The error term is just a C2H squared and then C4H4. So the next, okay, the standard difference formula is a second order approximations of. So let's go back to here. We are going to, so here from the very beginning, we just mentioned something that is the Taylor expansions here. And then we are going to use the Taylor expansions to divide the standard difference formula, right? The standard difference formula is here. Sorry, I'm going to use C2 tilde C4 tilde here. But here, for the center difference formula, I'm going to denote this as C2. And then this is the C4. And then later on, I'm going to use this center difference formula and its error to derive the Richardson's extrapolations derivative formula, finite difference formula. So here I'm going to use this result and then to derive another approximations of the derivative. So let's see, let's recall what we have here. So the standard difference formula is an approximation of the first derivative. And then this first derivative, it is written in this way. So this is the exact value. And then this is the standard difference formula. And then the standard difference formula is just the fx0 plus h, and then minus f0 minus h. I'm going to just use the notations to denote the formula here, but this is what the notations mean. The next thing is the C2H squared, and then plus the C4H4. And this is from the derivations we have here. So it's from the Taylor expansions, and then we get the error time. The error time C2, and then the error time C4. Does it make sense? But I replace, so this is the negative things, and then I would put it to the C2. This is subtraction, the negative sign with these things, and then I put it to C4. So I have the plus sign here in the formulas below here. So I got this, and then the next things, I am going to use this result to get a fourth order approximations of the first derivative. And what's this? Oh, this is the things I want to mention in the next week. So let's go back to here. This is, so can we make use of the standard difference formula to get a fourth order approximations of the first derivative? Yes, we can. So let's see the magic here. I'm going to use the standard difference formula and then do some operations here, and then to get a fourth order approximations. So let's see. This is, let's numerate this formula with number 3. So I am going to doing this, evaluating the third equation, the number 3 equation with step size h1/2. And then we would get this. So that is the same on the left-hand side, just the first derivative, and then equals to, instead of h size, we have the h1/2 of the step size. And then this is still the standard difference formula. And then C2 here, and then replace the h with h1/2, and then square. And then plus the C4 h1/2, and then to the fourth order. And so I got, what do I have here? So for this, I have D, and then H2, and then Z0, and then C2, and then 4H squared, C4, and then 16H4 for 4 order. So do we know what does it mean here? The notations meaning. So let's see, go back to here. I'm going to draw you a picture. Go back to here. Just go back to the last lecture, the previous lecture. So this is the picture. This is the standard difference formula, and then with the step size h. And the meaning of this, we just get the this one is the D H size and the fx0. This means that we are using the standard difference. The 0 means standard difference. This is with the step size h. And then we are going to use this slope here to approximate the slope here. And then what about the DH1/2? DH1/2 0 fx0. And this means that, okay, this is the step size h. Now we are not going to take this point, and then we are not going to take this point. We are going to take x0 minus 1/2 of h. X0 plus 1/2 of h. Does that make sense? So there are different data points here. We are going to use another data point. This one, x0 minus 1/2, x0 plus 1/2. And that's the data point we have here, data point here, and then we connect them. And then with a line, and then we are going to use this slope here to approximate to this slope here. And this is what the definitions or the meaning of this value. And it's just the replacing every h here in the formula, and then with the 1/2 of the h size. And then this is the f x0 plus h 1/2, and then minus f x0 minus 1/2 of the h. Any questions by so far? The meaning of the notation or the derivations here? No? Good. Good understanding. And no emotional damage. Okay. Good. Next, do you know the meaning of PhD? Getting a PhD is permanent head damage. Okay, good. Not very funny, right? Okay, let's go back here. Okay, we have the fourth equation. And then, so now we get the multiplications 4, and then subtract the number 3 equations. And then let's see, there's some magic happening here. On the left-hand side, we got 4 first derivative, and then subtract the number 3 equation. And then on the right-hand side, I get 4, but this is with the half step size. And then here I got C2 because this is C2 divided by 4 and then times 4. And then this one I get C4 divided by 16 and then times 4. So that's what I have below here, C2H squared, and then C4 4H4. And doing the subtractions, I just get the, it's with coefficients 1. So I get DH0 x0, and then plus the 2C2H squared, and then C4H4. Do you see the magic happening? On the left hand side, you get first derivative, but on the right hand side, originally in the standard difference formula, and then you would get the error is the dominated items is the H2. But here, for using some operations here, getting the intermediate step size formula and then doing some operations here, we are getting rid of the second order term. And then that's why we get a 4th orders approximations. We just have the error term here with 4th order. And that's the whole meaning, the whole things here. And let's go back to here in a few minutes after all the calculations. So on the left-hand side, we have 3 times the derivative of the f. So I'm going to divide both sides by 3. Divide by 3, and then on the left-hand side, I get just the first derivative. And then on the right-hand side, I got the formula. It should be the 4 times the half step size center difference formula, and then minus the full size of the center difference formula, and then divided by 3. And then what is the error here? Error is just 3 and the 4, and then this is the 3/4 because we have this is 104, one quarter, and then -1, and then I got subtractions, and then 3/4. But I'm dividing the both sides by 3, so here in the numerator, in the denominator, I should have 3 here. C4, H4. So at the end, you got, I'm going to write down the whole things here, and I give it another notation here, and then just this constant C. And it's just a constant. There's nothing very important for this constant, so I just denote it with another constant sign here. And then there's something wrong in my notation, sorry. So it should be this is the formula for the f function, so I need to get the f here, putting the f back to the notation, f here and the f here. There are a lot of wrong things here. The wrong notation f. Okay, good. And we also have, okay, good. I correct everything. And then let's go back to here. And then, so I got the formula and the error return. And the error return, what's the error return? The error return, it should be just the constant C and then H4. And which means that the dominated error return is in the order of 4. And this is what we have. This is called the Richardson's extrapolations formula. First derivative formula. First derivative finite difference formula. Formula. I want to write down the formula, but there's not so much space here. By the Richardson's extrapolations. Why do we call it extrapolations? Because you already see that we are doing something looks like interpolation here. We are making use extrapolate, so it's called extrapolations, the technique we use here. So let's see. I'm going to this part, you don't need to memorize it, the things below here. But I am going to explain the points we are using in this formula. So what I'm going to do here is to write out everything for that formula, for the standard difference formula here. And for the first one, we got the 4, and then the standard difference formula with the half size, it should be x0 plus h1/2, and then subtract the x0 minus 1/2 of the size, and then divided by 2h1/2, and then it's just the h size, because this is 2 and then 1/2. And the next things in the formula, it should be the f x0 plus h. This is the normal one with the normal step size, the whole step size, the entire step size. And this is 2h, and then divided by 3. I just write out the everything in this formula. This is the notation, and then write out specifically for the f function's value. And let's see. We are making use of 4.4 data to calculate the derivative. And that's what we have here. And the error is CH4. What data we are using? Let's draw out the line here. I got the line. And this is the line and the points. So we are actually approximating f prime x0 at the x0 point. And x0, f prime x0, this is what we want. And but we are making use of the points here. So first we get the point x0 minus h, x0 plus h. And these are the 2 points we are making use of. And there are 2 other points in the formulas. That is the x0 plus 1/2 of the step size. And then another point is x0 minus h, 1/2 of the size. And we are using the raw data here. That it means that we are going to use the f values on at this point. So as you can see here, we have made use of 4 points to approximate the first circuit. And so you know that we have a more accurate approximations of the first circuit, because we are making use of more points to calculate the W. So we are making use of more data, and then so that we are getting more accurate results. Does it make sense? Here, this Richardson's formula, we are making use of 4 points. And this is why we have more accurate result here. And then if you look back to what we have in the first step, in the backward difference and then center difference here, and then you would find out that we are just making use of 2 points, and then 2 points here. 2 points of the raw data, the f value, f functions value. And that's all the things I want to mention today. Is there are 4 minutes left, but I don't want to talk about the next chapter. So that's all the things. If you have any questions, you can come over to ask me. And your homework should be something about the Richardson's formula, and then it's also there should be another questions is about the optimal edge. Good. No more Uncle Roger. Let's type.